Hey guys, and welcome back to this class, Data Science, Deep Learning in Python, Part 2. In this lecture, we're going to talk about momentum, and I'm going to show you some code that implements it. And we're going to compare momentum to non-momentum gradient descent. If you want to just download this code without typing it out yourself, go to github.com/lazyprogrammer/machine learning examples and look in the folder ANN class 2. So the relevant files for this particular lecture are momentum.py and mlp.py. So mlp.py just contains some stock gradient descent MLP code. There are two versions of the MLP here. So you can use the sigmoid or you can use the rectifier linear unit. And so we covered how to derive all this code in the last class, Deep Learning in Python Part 1. And so the first thing we're going to do is we're going to run the momentum code on the sigmoid. The sigmoid version of the neural network. Okay, so I'm just going to walk you through all the stuff in this file. So we do our usual library imports. We import the stuff we need from util. So for this, we're going to use the full 784 dimensionality dataset, and the error rate, cost, and Y2 indicator stay the same. But we're going to get forward, and all the derivatives from mlp.py. I set the max iterations to 20 because we're going to do batch gradient descent, and I'm going to print every 10 steps. So I get the normalized data, x and y. These were pre-computed learning rates and regularization rates that I found. And the data is already shuffled, so I take the last 1000 and I make that the test set. I call Y2 indicator to turn my targets into matrices. Set the batch size to 500. So the number of hidden units that I want is 300. And in the previous lectures, I show you how I got this number. I'm initializing my weights to random small values. And so for test number 1, I'm going to do regular batch gradient descent. So I calculate what the batches are. I do a forward pass through the neural network, and I update with regularization and the derivative of the weight. And so if it's my print period, I do a forward pass through the test set. I calculate the cost. I append the cost to my array so I can print it later, and I also print it out to the console. I'm also keeping the error rates for some reason. So in test number 2, I'm going to do batch gradient descent with momentum. So I need this new momentum parameter, which I've set to 0.9. And I also need to keep track of the previous weight changes. So initially those are all 0. So these loops are all the same. I calculate the batches in the same way. The updates are a little different because I need to set the weight change variable, and I need to incorporate the momentum parameter. And the printing stuff is all the same. Calculating the error rate is all the same. So in test number 3, I'm going to use Nesterov momentum. So I use the same momentum parameter as last time. I initialize my weights in the same way, and I still have the previous weight changes that I'm keeping as variables. So the for loops, the way I calculate the batches is the same, and then the only thing that's changed here is how we do the momentum update. And then the printing stuff is all the same. And so at the final stage, I'm going to plot all 3 of the likelihoods on the same plot so you can compare them. So let's run this file. So you can see that with momentum, we beat the logistic regression benchmark. And also momentum goes much faster than just regular batch gradient descent. So if we compare the two types of momentum close up, you can see that they are pretty similar. Alright, so I've updated my MLP.py to use the rectifier instead of the sigmoid in the hidden layer. And so let's compare the results of this. Alright, so a couple things to notice here is that the ReLU neural network actually performs better than the sigmoid neural network, and faster. And we can zoom in to the log likelihood again. So the momentums are pretty much the same, and they both do much better than without momentum at all.